Tonight, I want to show you something that is moving right now. Not a meteor. Not a satellite. Something so large that it takes millions of years to notice it change. A galaxy. A city of stars that drifts, turns, and sometimes meets another city of stars. This is Curious Nights. And tonight's episode is called The Slow Dance of Galaxies. We'll move gently and clearly. We'll start with one idea you can hold on to. Galaxies are not fixed decorations. They are travelers. And their meetings shape the universe we see. To understand the dance, we should first understand the dancers. A galaxy is not a single object. It's a system. Stars, gas, dust, and darker components we can't see directly, held together by gravity. Some galaxies are spirals. Some are smooth and rounded, like ellipses. Some are irregular, as if still assembling themselves. What matters tonight is motion. Inside a galaxy, stars orbit the center. Gas clouds drift, collide, and compress. New stars ignite in quiet bursts of blue light. And the whole galaxy moves through space, too. Not like a ship through water. More like a slow current in a vast, invisible sea of gravity. So when we say, the slow dance of galaxies, we mean two things at once. Their internal turning, and their long approach toward one another. Here's a detail that keeps people watching this story. When galaxies collide, the stars almost never hit each other. It sounds impossible. Two galaxies overlapping, and hardly any direct star-to-star impact. But stars are tiny compared with the distances between them. So what actually collides? Gravity fields, orbits, and gas. Gas clouds can slam together, heat up, and compress. That compression can trigger star formation. So a galactic encounter can light up new regions of space with young stars. And yet, it's still a gentle event in human terms. Not gentle in energy. Gentle in pace. A drama played at a speed that forces patience. Now, for attention, let's bring the dance closer. To a story that includes us. The Milky Way is not alone. Nearby is the Andromeda Galaxy. And the two are moving toward one another. This is not something you can watch unfold in a lifetime. But it gives the whole idea a spine. Galaxies are not only distant. They are part of our future sky. Over very long times, the shapes we recognize can change. Spiral arms can stretch and distort. Long streams of stars can be pulled out like luminous ribbons. And eventually, the two systems can settle into something new. A merged galaxy with a different structure. Different star-forming regions. a new night sky for whatever observers exist then. When astronomers model galaxy encounters, a pattern appears. It's not always identical, but there are common steps. First, the approach. Two galaxies drifting closer in the dark. At first, their shapes look unchanged, but their outer stars begin to feel the tug. Then, a close pass. This is where the most dramatic distortions begin. Tidal forces pull out long tails of stars and gas. Bridges can form, connecting the two galaxies in a faint arc. After the first pass, they may separate again. Not because the dance is over, because the momentum carries them outward. But gravity is patient. They fall back toward each other, again and again, losing orbital energy. Eventually, they settle. Two dancers becoming one. There is another partner in this dance. One you cannot see with your eyes. Galaxies are thought to sit inside larger halos of dark matter. Dark matter doesn't shine, but it adds gravity. It helps shape how galaxies move and how they hold together. On the largest scales, galaxies are arranged in a cosmic web. Filaments, clusters, and vast spaces between them. So the dance is not random. It happens along these large gravitational structures. This can be a calming thought, if you let it be one. Even immense motions have a kind of structure. Like tides. Like seasons. Only on a scale the mind has to approach slowly. Let's gather the story in a quiet way. Galaxies turn and travel. They approach one another slowly. And when they meet, the stars mostly pass like ghosts. What changes is the pattern. Orbits are reshaped. Gas clouds collide and compress. New stars can ignite, briefly brightening the encounter. And far in the future, our own Milky Way continues its approach toward Andromeda. Not as a threat, as a reminder that change is built into the sky. For the last few moments, you can picture two galaxies as soft spirals of light. Turning, drifting closer, pulling out long, faint ribbons, then settling into a new, quiet shape. You don't need to hold onto the details. Just the feeling of a universe that is alive with slow motion. A dance you can't watch in real time, but can still understand. Good night. Tonight, I'd like to take you outside for a moment. Not far. Just to a quiet place near a window, or a back garden, where the air feels still. Imagine Jupiter as a bright, steady lantern in the dark. And beside it, 4 tiny points of light. Small enough to miss if you don't know to look, but persistent once you do. This is Curious Nights. And tonight's episode is called Jupiter's Moons, 4 tiny worlds with big personalities. We'll move slowly. We'll meet Io, Europa, Ganymede, and Callisto. And we'll keep coming back to one soothing thought. In space, even small worlds can be complicated. Let's begin with the first hook in this story. 4 lights that refuse to stay put. In the early 17th century, Galileo Galilei aimed a telescope at Jupiter. And he saw points of light nearby, changing position night after night. At first, they could look like ordinary stars. But stars don't arrange themselves in a neat line beside a planet, and then swap sides in a steady rhythm. What he was seeing was simple and profound. Moons orbiting something other than Earth. A miniature system, moving according to its own center. Tonight, we're not here to rush through dates or arguments. Just to notice the feeling of that discovery. A bright planet, 4 companions, and a pattern that quietly changes how you think the universe is organized. If these moons were only rocks circling a planet, we wouldn't still be talking about them. What makes them unforgettable is that each one behaves like its own world. Io is the restless one. Europa is the quiet one with a secret. Ganymede is the large one, with its own internal strength. And Callisto is the old one, scarred by time. And here's the retention trick that also happens to be true. They are linked. Not emotionally, of course, but physically, by gravity. Their orbits interact in a stable rhythm called a resonance. It's like a repeating beat that keeps them in step. And that steady beat helps shape their interiors. It helps decide which moons stay warm inside, and which grow quiet and cold. Let's meet Io first. Because Io is impossible to ignore. Io is the most volcanically active world we know of in the solar system. Its surface is reshaped again and again by eruptions. Not a gentle geological pace, a relentless one. Why would a small moon be so energetic? The key idea is tidal heating. Jupiter's gravity pulls on Io. And because Io's orbit is influenced by its neighboring moons, that pull varies. So Io is flexed, over and over. Like a paperclip bent repeatedly. Only here the bending happens in rock. And the heat has to go somewhere. If you picture Io in the dark, you can almost imagine faint, hot points on its surface. Not city lights. Volcanic fire. A world that cannot quite sit still. Now, Europa. If Io is heat on the outside, Europa is motion hidden under ice. Europa's surface is bright and smooth compared with many moons. And it is crossed with long, dark lines and fractured patterns. Those cracks are part of what makes Europa so compelling. They hint that the ice shell has shifted and moved, that something has pushed from below. Scientists have multiple lines of evidence suggesting Europa may have a global ocean beneath its ice. We should keep the language careful. We are not listening to waves directly. We are inferring from measurements, from magnetic effects, and from the surface itself. But even the careful version is extraordinary. A dark ocean, sealed away from sunlight, possibly warmed by the same gravitational flexing we just talked about. And in that thought, you can feel why Europa holds attention. It is a quiet invitation to imagine chemistry, time, and maybe, one day, life. Now we come to the last two of the four. And they changed the mood again. Ganymede is the largest moon in the solar system. It's bigger than the planet Mercury. And it has something unique among moons: a magnetic field of its own. A magnetic field suggests an active interior. Some kind of moving, electrically conducting material below the surface. It's another reminder that these are not passive lumps of ice and stone. Callisto, by contrast, feels like a record of time. It is heavily cratered. Its surface looks ancient and quiet, less reworked by internal heat. And still, Callisto has its own interest. Even a world that seems inactive can hide layers and complexity beneath a calm exterior. In a set of 4 moons, Callisto plays an important role. It shows us what it looks like when a world mostly keeps its old scars. Let's gather the 4 moons gently. Io, hot and constantly reshaped. Europa, bright ice with a hint of an ocean below. Ganymede, vast and quietly powerful. And Callisto, old and cratered, holding its history on its face. What keeps the story coherent is gravity. Not just Jupiter's pull, but the way the moons tug on one another in repeating rhythms. That rhythm helps decide which interiors stay warm enough to move. And now we can let the science soften into a picture. A bright planet hanging in the dark. 4 small worlds circling it like companions, each with its own pace, each with its own texture, each quietly insisting that a moon can be a world. You don't have to keep any of the names, just the feeling that there are places out there that are small in the sky, but enormous in detail. Good night. Somewhere in the center of our galaxy, there is a region of space where gravity becomes so strong that even light cannot escape. It is completely invisible. It makes no light of its own. And yet it contains the mass of more than 4 million suns. This is a black hole. Tonight, we'll slowly explore what black holes really are, how they form, what happens near their mysterious edge, and why they may hold some of the deepest secrets of the universe. A black hole is one of the strangest objects in the universe. It is not a hole in the usual sense. It is a region of space where gravity has become incredibly powerful. So powerful that nothing can escape once it passes a certain boundary. Not dust, not gas, not even light itself. Because light cannot escape, the object appears completely dark, which is why we call it a black hole. Most black holes begin their story as enormous stars. Stars live for millions or sometimes billions of years. During their lifetime, they produce energy through nuclear fusion. Inside the core of the star, hydrogen atoms combine to form helium. This reaction releases tremendous energy. That energy pushes outward. Gravity pulls inward. For most of a star's life, these forces remain balanced. Eventually the star runs out of fuel. Without fusion pushing outward, gravity begins to take over. The core collapses rapidly. For the most massive stars, this collapse becomes unstoppable. The matter is compressed into an incredibly small region. Gravity becomes stronger and stronger. Eventually, a black hole forms. Every black hole has a boundary known as the event horizon. This is often described as the point of no return. If an object crosses this boundary, escape becomes impossible. The escape velocity becomes greater than the speed of light. And because nothing can travel faster than light, nothing can come back out. Black holes do more than simply pull objects inward. They warp the very fabric of space and time. According to Einstein's theory of general relativity, massive objects bend space-time. Near a black hole, this bending becomes extreme. Time itself begins to slow down. If you were observing someone falling toward a black hole, their clock would appear to tick more and more slowly. To a distant observer, the falling person would seem to slow down near the event horizon. Eventually they would appear almost frozen in time. This strange effect is called gravitational time dilation. Although black holes themselves are invisible, the area around them can be incredibly bright. Gas and dust falling toward a black hole begin to spin. They form a glowing structure called an accretion disk. As the material spirals inward, it heats to extraordinary temperatures, sometimes hotter than the surface of stars. Some black holes are far larger than those formed by collapsing stars. These are called supermassive black holes. They can contain millions or even billions of times the mass of the Sun. Almost every galaxy appears to contain one at its center. The Milky Way's central black hole is called Sagittarius, a star. In 2019, scientists captured the first image of a black hole. This was achieved by linking radio telescopes across the entire Earth. Together they formed a virtual telescope the size of our planet. The image revealed a glowing ring of light surrounding a dark center. The shadow of the black hole itself. In the 1970s, physicist Stephen Hawking proposed something surprising. Black holes may not last forever. Through a process now called Hawking radiation, black holes can slowly lose energy. Over extremely long periods of time, they may eventually evaporate. Imagine drifting slowly through space toward a black hole. At first, it might not look very different from any other region of the universe. But as you move closer, something unusual begins to happen to the light around you. The gravity of the black hole bends space itself. And because light travels through space, its path bends as well. Distant stars would appear distorted, their light stretched into curved arcs around the darkness. This effect is known as gravitational lensing. The black hole acts almost like a cosmic magnifying glass, bending and focusing light from objects behind it. Near the edge of the event horizon, the view would become even stranger. Light from every direction could wrap around the black hole, allowing you to see parts of the universe that would normally be behind you. Some black holes are surrounded by enormous clouds of gas and dust. As this material falls inward, it forms a rapidly spinning accretion disk. Friction within the disk heats the gas to extraordinary temperatures. The result is an object known as a quasar. Quasars are among the brightest things in the entire universe. Some release more energy than hundreds of billions of stars combined. Yet all of that light ultimately comes from matter slowly falling toward a black hole. These distant beacons can be seen across billions of light years, meaning the light we observe today began its journey when the universe was still young. Black holes also inspire some of the most intriguing ideas in theoretical physics. One possibility is something called a wormhole. A wormhole would act as a shortcut through space-time. Instead of traveling across vast distances, space itself would fold, connecting two distant points. Some equations in general relativity allow solutions that resemble these tunnels. However, scientists believe that real wormholes would probably be unstable. If they formed at all, they might collapse almost instantly. For now, wormholes remain an idea, a fascinating possibility that continues to inspire research and imagination. Black holes are often imagined as cosmic monsters, but in reality, they are quiet objects. They drift through galaxies. They shape the motion of stars. And they reveal the strange behavior of space and time. Perhaps one day they will help us understand the deepest laws of the universe. Until then, they remain one of the most fascinating mysteries in the cosmos. Good night. Tonight's journey through space will be quiet. No dramatic countdowns. No rushing through discoveries. Instead, we'll slowly explore a collection of calm and fascinating facts about the universe. Space is often described through extremes: exploding stars, colliding galaxies, black holes with enormous gravity. But much of the universe is surprisingly gentle, slow, quiet. Stars drift across the galaxy over millions of years. Planets follow calm and predictable paths. Light travels peacefully through the darkness between worlds. This is Curious Nights. And tonight we'll explore some of the most relaxing facts about space. Small pieces of cosmic wonder, without the intensity. One of the most peaceful facts about space is that it is almost completely silent. Sound needs something to travel through. Usually air or water. But the space between planets and stars is mostly empty. Atoms exist there, but they are extremely spread out. If you could somehow float safely between the planets, you would hear almost nothing at all. No wind, no rustling leaves, no distant echoes, just stillness. Planets move through space in remarkably steady patterns. Each planet follows an orbital path around the Sun, a path shaped by gravity. Earth completes one orbit every 365 days. Mars takes about 687 days. And far beyond the inner solar system, Neptune completes just one orbit every 165 years. These quiet motions have continued for billions of years. A slow celestial dance. When you look at the night sky, you are seeing light that has traveled an incredible distance. The light from the Sun takes about 8 minutes to reach Earth. The nearest star beyond our Sun is Proxima Centauri. Its light travels for more than 4 years before reaching us. Other stars you can see in the sky may be hundreds or thousands of light years away. The light arriving tonight may have started its journey long before modern cities existed. A quiet beam of ancient starlight finally arriving on Earth. Saturn's rings are one of the most beautiful structures in the solar system. From far away they appear smooth and solid. But in reality the rings are made of countless pieces of ice and rock. Some are tiny grains, others of the size of houses. Each fragment follows its own orbit around Saturn. Together they form a thin, shimmering disk that stretches hundreds of thousands of kilometers across. Yet the rings themselves are surprisingly thin, often only a few tens of meters thick. Stars are born inside enormous clouds of gas and dust called nebulae. These clouds can stretch across dozens of light years. Inside them, gravity slowly gathers material together. The process is incredibly slow. A single star may take millions of years to fully form. Eventually the core becomes hot enough for nuclear fusion to begin, and a new star quietly ignites. Jupiter is the largest planet in our solar system. More than 11 Earths could fit across its diameter. Its gravity is so strong that it helps shape the entire solar system. Jupiter also has dozens of moons. Some are icy worlds. Some are volcanic. And some may hide oceans beneath their frozen surfaces. The Milky Way galaxy itself is slowly rotating. Our solar system orbits the center of the galaxy once every 230 million years. That means the dinosaurs lived during a completely different part of our galactic orbit. Since Earth formed, the Sun has circled the galaxy only about 20 times. The atoms in our world have an ancient origin. Hydrogen formed shortly after the Big Bang. Heavier elements like carbon and oxygen were forged inside stars. When massive stars exploded as supernovae, those elements were scattered across space. Eventually they became part of new stars, planets, and even living things. The universe is often described through powerful events, but much of it unfolds quietly. Planets orbit slowly. Stars shine steadily. Galaxies drift through the darkness. A calm rhythm that has continued for billions of years. So tonight, as the sky grows quiet above you, remember that you are part of this vast and gentle universe. Endlessly large, quietly beautiful. Good night. Tonight, we'll follow one of the longest stories in the universe. A story that unfolds over millions, sometimes billions, of years. It begins not with light, not with heat, but with darkness and dust. Across the Milky Way galaxy, enormous clouds of gas drift slowly through space. These clouds can stretch across dozens of light years. They are cold, quiet, and almost invisible. Yet hidden inside them is the raw material for something extraordinary. Stars. This is Curious Nights. And tonight's episode is called The Life Cycle of a Star, From Dust to Dust. We'll gently trace the long path a star takes, from drifting clouds of cosmic dust to brilliant shining suns, and eventually back into the dust again. Most stars begin their lives in regions astronomers call stellar nurseries. These nurseries are enormous molecular clouds. They contain hydrogen gas, tiny grains of dust, and traces of heavier elements. The temperature inside them can be extremely low, sometimes only a few degrees above absolute zero. In such cold conditions, atoms move slowly. The cloud drifts through the galaxy almost peacefully. But gravity never rests. Even the smallest imbalance in the cloud can begin a slow collapse. A region that becomes slightly denser than its surroundings begins to pull in more material. Gas gathers. Dust follows. The region slowly grows heavier. As gravity gathers more and more material, the center of the collapsing cloud becomes denser. The growing object at the center is called a protostar. It is the earliest stage of a star's life. Material continues to fall inward toward the center. As it does, the energy of the falling gas turns into heat. The core temperature slowly rises, thousands of degrees, then tens of thousands. A disk of gas often forms around the young protostar. Inside this disk, planets may one day begin to form. Eventually, the core becomes hot and dense enough for something remarkable to happen. Nuclear fusion begins. Hydrogen atoms begin combining to form helium. In that process, a small amount of mass is converted into energy. That energy becomes light and heat. It pushes outward against the inward pull of gravity. When these forces balance each other, the star becomes stable. A new star has officially begun its life. The longest chapter of a star's life is called the main sequence. During this stage, hydrogen fusion in the core produces a steady flow of energy. The star shines steadily for millions or billions of years. Our own Sun is a main sequence star. It formed about 4.5 billion years ago. And it is expected to remain stable for several billion years more. Stars can vary enormously in size. Some are smaller and cooler than the Sun. Others are dozens of times larger and far brighter. Eventually, even a stable star begins to change. The hydrogen fuel in its core slowly runs out. Without that fuel, the balance inside the star shifts. The core contracts and heats up. Meanwhile, the outer layers expand outward. the star grows enormously larger. It becomes what astronomers call a red giant. The final stage of a star's life depends mostly on its mass. Stars similar to the Sun shed their outer layers into space. This glowing cloud is called a planetary nebula. At the center, a dense white dwarf remains. A hot stellar core slowly cooling over billions of years. More massive stars end their lives more dramatically. Their cores collapse, and the outer layers explode outward in a supernova. These stellar endings are not simply the end of a story. The material released by dying stars spreads into the galaxy. Gas and dust slowly mix with the interstellar medium. Over time, new clouds form. Gravity gathers the material once again. And the cycle begins again. New stars forming from the ashes of older ones. The atoms in our bodies were forged in ancient stars. And long in the future, they may become part of new stars once more. From dust to star, and back to dust again. Good night. Tonight, we're going to spend some quiet time with one of the most recognizable sights in the solar system. Saturn and its rings. From far away, the rings look smooth and solid. A thin, shining band wrapped neatly around a pale planet. But when scientists look closer, the picture becomes softer and stranger. The rings are not a sheet. They are countless pieces of ice and rock, moving together in a patient orbit. This is Curious Nights. And tonight's episode is called Sleepy Facts About Saturn's Rings. We'll move slowly. We'll explore how the rings formed, what they're made of, and the quiet patterns that keep them in motion. One of the gentlest surprises about Saturn's rings is this. They are incredibly thin. From a distance they look wide and solid. But their thickness is often measured in tens of meters. That's remarkably slender compared with their enormous width. And the rings are not a continuous plate. They're more like a moving swarm. Billions of icy particles, each following its own orbit around Saturn. Some pieces are as small as grains of sand. Others of the size of houses. Most are made mostly of water ice, which reflects sunlight beautifully. So the rings glow not because they produce light, but because they scatter sunlight back into space. A quiet field of drifting mirrors around a distant planet. If you could fly closer to Saturn's rings, you'd notice something else. They are divided into many separate bands. Scientists label the main ones with letters. The A ring, the B ring, the C ring. Between some of these bands are gaps. One of the most famous is the Cassini division. From afar it appears like a clean break in the rings. But even the gaps are not truly empty. They still contain particles, just fewer of them. The rings are better imagined as a pattern of crowded lanes and quieter lanes. Another gentle fact about Saturn's rings is that they are not left alone. Small moons orbit nearby. These moons act like quiet guides. Their gravity nudges ring particles into certain paths. A few of them are called shepherd moons because they help maintain narrow ring edges. Their gravity keeps particles from drifting too far away. As they orbit, they create waves and ripples through the ring material. Not ocean waves, but patterns in the density of particles. It's a quiet choreography. Moons and ice fragments shaping each other through gravity. A system that looks calm from afar, yet constantly rearranges itself. Scientists still discuss exactly how Saturn's rings formed. But several ideas appear again and again. One possibility is that a small moon wandered too close to Saturn. When objects approach within a certain distance, tidal forces can pull them apart. Instead of remaining a single body, the moon might break into countless fragments. Those fragments would spread into orbit, gradually forming rings. Another idea is that the rings formed from leftover material during Saturn's early history. Small icy pieces that never quite assembled into a moon. Either way, the rings tell a quiet story about gravity. How it builds worlds. And sometimes, how it gently pulls them apart. Another quiet truth about Saturn's rings is that they are temporary. Not temporary for us, but temporary in cosmic terms. Over time, ring particles collide with each other. Some slowly spiral towards Saturn. Others may escape the ring system entirely. Scientists sometimes describe this process as ring rain. Charged particles drifting inward along Saturn's magnetic field. So the rings are not frozen in time. They are evolving, slowly thinning and rearranging themselves over millions of years. So when we picture Saturn's rings, it helps to soften the image. Not a rigid halo, but a vast orbiting field of ice. Billions of pieces drifting together. Some tiny, some enormous. All quietly circling a distant planet. Moons pass nearby and sculpt the edges. Gravity shapes waves and gaps. And sunlight glints from icy surfaces. For the last few moments, imagine Saturn hanging in the dark. A pale world with wide, luminous rings. Slowly turning. Patiently orbiting the sun. You don't have to remember the details. Just the picture. A quiet system of ice and gravity. drifting gently around a distant planet. Good night. Tonight, we're going to follow a small object into very large darkness. Not a monument. Not a flag. A record. In 1977, 2 Voyager spacecraft left Earth, carrying a gold-plated copper disc meant to outlast all of us. A message in sound and picture, made for a listener we could not imagine clearly. This is Curious Nights. And tonight's episode is called How the Voyager Golden Record Was Made. We'll move slowly. We'll stay with the practical details, the human decisions, and the quiet ingenuity of turning a planet into a playable object. The Golden Record was, in a sense, a time capsule. Not aimed at a particular star. Not addressed to a known civilization. More like a carefully packed bottle, placed into an ocean with no shore in sight. NASA asked a small committee to decide what to include. Carl Sagan chaired the effort, with collaborators including Frank Drake, Andrew Yan, Timothy Ferris, and the designer John Lomberg. The challenge wasn't only technical. It was philosophical. If you have a limited amount of space, what do you send to represent a world? They chose to send 3 kinds of things: sounds, music, and a set of images encoded in an audio-like signal. And they added something else, too. Instructions. Because a message isn't really a message, unless it can be decoded. Before we talk about what's on the record, it helps to picture what it is. A real disc, with grooves. Like a phonograph record from home. NASA describes the record as a 12-inch, gold-plated copper disc. It's protected by an aluminium cover, which carries the playback diagrams. There is also a small and striking detail. An ultra-pure sample of uranium-238 was placed on the cover. Because uranium decays at a known rate, it can serve as a kind of clock. This is one of those design choices that feels almost tender. Not just, here is what we are, but also, here is when we were. The cover isn't decorative. It's an instruction sheet in symbols. A calm attempt to be understood without shared language. NASA explains that the diagrams show how to play the record, and how to reconstruct the images. One part describes the picture signal as a series of lines, similar in concept to the way television scanning builds an image. Another part of the cover points outward. It gives a way to locate our Sun, in the larger galaxy. And it anchors the message in time, using that uranium clock. Historically, this is important to remember. The Golden Record is not only a playlist. It is also a compact engineering argument that says, if you can measure and build instruments, you can probably decode this. Now we come to the part people remember. What did they choose to put on it? NASA lists 115 images, along with natural sounds like surf, wind, thunder, birds, and whales. They included spoken greetings in many languages, spanning ancient and modern tongues. And then there is the music. A selection meant to hint at the range of human expression, without pretending to be complete. Any list would be imperfect. So the task becomes something else. A careful sample. This is where the episode can stay balanced. Historically, we can say there was a real committee with real constraints and deadlines. And gently, we can imagine the feeling of making those choices late at night. Trying to be honest. Trying to be generous. Trying not to turn Earth into a slogan. Choosing the contents was only the first half. The other half was making it physical. Making it playable. The images weren't stored as photographs. They were encoded into a signal that could be etched into grooves. Brightness values were mapped into the sound-like pattern, so that a decoder could reconstruct pictures from the audio information. And then the manufacturing had to be done with care. NASA describes work at a record processing center in Gardena, California, where the records were cut and plated. It's a lovely contrast. Cosmic ambition, built with the same industrial precision used to make ordinary records on Earth. Except this time, the record wasn't meant to last for years. It was meant to last for ages. So that's the shape of it. A gold-plated copper disc, sealed behind an aluminium cover with a small map of how to listen. A committee choosing sounds, images, languages, and music, with limited space and finite time. Engineers and technicians turning those choices into grooves that could survive the cold and silence of space. And beneath it all, a quiet human gesture. The willingness to be known. Even if no one answers. For the last few moments, you can picture the record as it travels. No engine noise. No wind. Just a steady drift through a dark that doesn't hurry. You don't need to hold on to any details. Just the feeling of careful making. And the idea that even technical work can carry something like tenderness. Good night.